Okay, let's start with section number 6, power flow analysis. All right. So why is power flow analysis important? Because power flow analysis is the foundation of all power system study analysis. So if you check this terminology, some papers, if they published like 10 to 20 years ago, they may call power flow analysis as load flow analysis. I personally prefer power flow analysis because power flow means really the power flowing through a transmission grid or power grid. But load flow means the power is flowing to power some load. I guess in the past, when the system topology is very simple, most of the system is like a radio network. You have generation on one side and load on the other side. So those load will need some flow, right, of the energy to be power. So it's okay to call that load flow analysis. But I personally suggest power flow analysis is the right terminology. So the goal of the power flow analysis is very simple. It's just to determine the voltage, phasor, and the complex power for every single bus. So if you're able to determine the voltage, phasors, and complex power, voltage phasor include the magnitude angle, complex powers include the real power and the reactive power. If you can do that for every single bus of the network, you actually solve the power flows. You finish the power flow analysis. Definitely, you can add some additional requirements. For instance, I know the power flows right now for the current system, but I want to open the line. So if I open the line, definitely the current on the line will become 0. So the voltage on the both sides of the line will change. So we need to recalculate the power flow, right? So that also indicate some applications of power flow analysis. Or in a more complex design, you can simulate the dynamic of the system. The system keep changing under a number of contingencies or disturbances. At each stage, you need to recalculate the power flow. So that's why the power flow analysis is very useful in power system study. Here we have to make clear about some assumptions we make for the power network on which we are going to solve power flows. The first, this system has to be in steady state. This is the assumption, the fundamental assumption about the power flow model analysis. But when we apply the power flow analysis to different applications, so in some applications, the system may not be exactly in the steady state. If it's close to the steady state, the power flow result will be still meaningful. They just still represent an approximation about the system condition. If the system is perfectly in the steady state, the power flow result is completely trustable, okay? But if the system is not in steady state, but in somehow dynamic state, which means the voltage changing, the frequency can also change. For instance, if you remember the assumption we make for to create the concept of phasor, we mentioned the system need to operate at a constant frequency, such as when we write the voltage or current phasor, we don't need to write that omega. We assume that omega to be always 2 pi times 60 hertz, right? But in some studies, the frequency will change around 60 hertz as long as the change is very small. It doesn't affect the concept of voltage phasor. We still can utilize voltage or current phasor to represent the waveform. So we still can do the power flow analysis on such model. So the requirement will be, ideally, you want to have the system in steady state. If it's not in perfectly steady state, it need to at least have well-defined voltage and current phasor. So that's a bottom line requirement. So if you have the well-defined phasors, you can utilize all the methodologies and models we're going to talk about in this session. So next assumption, we hope the system to be balanced if it's a 3-phase power network. Because power flow model is based on single-phase system. If you have phases A, B, and C, if it's a perfectly balanced, there's no difference to calculate power flow in A, B, or C. So you can pick any one. So we'll focus on single phase network. But if the system is not in balance condition, it doesn't mean the power flow analysis is completely wrong. It's just not that accurate. But you still can utilize power flow analysis to do some calculation. One example is if the system is not balanced. For example, for instance, you have a short circuit. The short circuit is added to just single phase. Okay, you want to do the calculation after the short circuit. Definitely you cannot pick just single phase, because if you pick A, where the fault is added, phase B and C will be different. So there's a methodology which is called a sequence component method, which can decompose the system network into a 3 fictitious network. So one network represents the balanced part, which is called positive sequence network. The second is unbalanced part, which is the negative sequence network. And the third one is called zero sequence, which is basically, you can think about if there's a sharing between the phase A, B, and C. So the transformation from the 3-phase network A, B, and C to the sequence network is accurate. So you still can use power flow analysis to each sequence network for the positive or negative or zero. They will give you some indication about what the post-fault system can be. Even it's not maybe 100% accurate, but it's still very useful. It's very, very quick, much faster than simulating the 3-phase network at a very tiny time step, right? So which means the power flow analysis can be applied to many studies, not just a steady state and balance condition, but definitely if the system is in steady state and the network is perfectly balanced, the power flow result will be very accurate. How do we model substations? If you have opportunity to visit any substation, you will be able to see some layouts. The layout just show how the line is connected to the substation. It will be coming from which direction. It will connect to which circuit breaker, right? Between the two, even within the substation, on the power network, just single point, just single node. But actually, it's another whole system. It can be very complex. They can have tens of circuit breaker, separate line by line, equipment by equipment. But in the power flow analysis, we don't go into the detail of each substation. We treat substation simply as node. Or a better word is bus. Bus means it can deliver power or receive power in many directions. So you can connect many lines to the same node. Node, just think about is like a dimensionless point, but which is not accurate. The bus itself in power system can be another power system, smaller scale power system, but usually we call it a bus. A bus can be connected to a generator. So in such case, we call that bus as generator bus. If it doesn't connect to generator, it need to connect to some load. Even in the power flow model, the load can be ignored, but usually we can call any bus without the generator as a load bus. Transmission lines and transformers are modeled as branches. If you remember, for the transmission line models, we can convert all lines, no matter it's a short line, medium line, or long line, into a pi model. Okay, so for the short line, medium line, when we take the pi model, it can be accurate. So the impedance will tell the actual impedance. For short line, we can even ignore the capacitance to the ground. All right, we only just keep a single impedance. But when we take the pi model for long line, you need to convert the impedance, the Z, into Z prime, right? The Y into Y prime. Then you can use pi model. For transformer, basically just modeled by reactance. You can treat transformer as some like short line. It was similar to short line. But the one tricky part introduced by transformer will be the the phase shifting. So if this transformer is phase shifting transformer, it can introduce the phase shift. So we need to cover that to talk about how we can model that one more accurately. But in general, we can treat transmission lines and transformer as branches. Branches is just a single line connecting, each branch is a single line connecting two nodes or two buses of the system. So next, we want to make a calculation be easier, especially for the convenience of coding. If you want to program power flow analysis by some software, we don't want to deal with their physical unit about either kilovolt or maybe a volt or ampere or kiloampere or megawatt or kilowatt, right? So we don't want to deal with units. So we want to convert everything to per unit. Then we need to choose a base. For power, we have to select a common base for the entire system. Okay, you already get some a flavor of finding the common base in the section number 5, right? When we want to figure out the per unit circuit in the midterm exam problem. So usually we use 100 MVA as a common base, and we can choose the voltages for different equipment at the voltage base. Then we will convert everything to per unit. All right, so this is now the first lecture we deal with a power flow problem. Actually, if we go back to the section 2 from the basic principle sections, we already talked about how to solve power flow, but we just create a very simple problem. If you still remember this example, it has the 3 sources connected at 3 buses, right? And there will be a 3 transmission line connecting those 3 buses. For this example, we make some assumption. We assume the voltage magnitude everywhere is same. Then we try to solve. We gave some injection. We gave some generation at some buses. For example, this generation is 1 + 1J, which means active power is 1. So if you use 100 MVA as a power base, we immediately know the active power or real power is 100 megawatt. Reactive power is 100 megawatt. That's what we know. Okay, because the common base, this one will be 15 megawatt real power and 50 megawatt reactive power. So for this one, that indicate the capacitor. Capacitor is a reactive source. So the final calculation will tell, by using the base, we know this one provide 100 megawatt reactive power. So for this question, we want to calculate the line flows of complex power. So for instance, it gave you some line flow. Because we assume the voltage magnitude everywhere to be same. And if you go back to that slide, actually we prove the active powers sent from both ends will be opposite to each other. Okay, that makes sense because if the lines, each line is lossless, whatever you send from bus 1 will completely receive from bus 2. If you define the direction to be from both terminals, so their number have to be opposite to each other. And the reactive power will be equal. This one was approved on that slide, but later we have a more analysis about why this is true. When the system the line is lossless and the voltage on the both sides are equal, which means both terminals will send the reactive power to the middle. So they will come to the middle of the line, right? So they will maintain the voltage on the both sides to be the same. So by making such assumption, we can solve power flow using just the theory about the circuit. But the more general power flow problem may look like this one. Okay, so you have 3 main buses, and also there's another bus only connected to a bus 3. So you have 4 buses. Bus 1 and bus 2 are connected to 2 sources. bus 4 is connected to a load, and bus 3 is connected to not generator load. So basically just bus 3 just connecting the other 3 buses. For this case, we give impedance of each line. Assume it is each line is a short line, we only have impedance. And also for bus 1, we gave it the voltage magnitude, but we don't know the angle. For bus 2, we know the P, active power, and also the voltage magnitude, but we don't know angle and we don't know Q. Okay, and for bus 4, we know both P and Q. Those 3 buses are very typical types for some general buses. For instance, bus 2, if for what bus we only know active power and voltage, but not the reactive power and angle. This is pretty much generator. If it's a generator bus, we can control the active power. Okay, so we'll talk about how to control the active power or dispatch among multiple generators in the next session, in the session number 7, for the optimal dispatch section. And for each generator, I can decide what voltage I need to operate. So I have an exciter or automatic voltage controller. I can set up the setting point for the voltage. So 1.05 means this generator, the terminal voltage will be slightly higher than the base value. So it'll be about 5% higher. So this one can make the generator to generate some reactive power for the neighbor buses. And this bottom bus, number 4, is basically just a load bus, because we know both P and Q. You see the power is going to some customers, but we don't know the voltage, because voltage will depend on the voltage of the rest of the system. So this is a typical load bus. And for the bus 1, we only know the voltage magnitude, but we don't know power, because this bus very likely will represent what we call slack bus. Slack bus means or balancing bus, which means this generator can be very flexible. Its output depends on the net power of the entire network. Okay, so if for the rest of the system, if you calculate the total P and total Q, if that's not 0, that one will be compensated by bus 1. Okay. Yeah. So later we'll come back to those 3 types. So the objective power flow is try to solve for each bus in this figure, no matter which types they fall into. We have to for this bus we need to know the Q and the angle for bus number 2, and for bus 4 we need to know the voltage and angle, and for bus 1 we need to know angle, P and Q. Actually, there's also the bus 3, right? The bus 3 doesn't connect directly to any load, but actually we know this is also a load bus because the P and Q are both 0. It's just simply 0. So we still need to solve the voltage and angle at that bus. Okay. All right. Yeah, let me talk about how we are going to model each bus. Let's just consider we just pick bus 1 from that circuit because that's pretty typical. It has a source. It has 2 branches going to the other 2 buses. Okay, so for bus 1, we use capital E1 to indicate the voltage, internal EMF of that generator. And the Z10 means the impedance connecting that EMF to the terminal, which is the synchronous reactance, right? If we also consider the resistance, it will be the synchronous reactance plus the resistance, the armature resistance of that generator. And for each branch, we have impedance. So Z12 just indicate impedance from bus 1 to bus 2. And Z13 will be from bus 1 to bus 3. In general, those both impedances actually a complex value, not purely imaginary. They can have a resistance and also reactance. Okay, and for the convenience of calculation, usually we don't use the impedance. I will explain why we want to change everything to the admittance. Because when we change everything to the admittance, we make a matrix about the entire network. That matrix is sparse network, sparse matrix. So it's more convenient for storage of the data. So there are two steps we need to do for each bus. The first step is we simply apply the Kirchhoff current law. By using the Kirchhoff current law, we just simply write on the left-hand side will be current going to the system. On the right-hand side will be the current coming into this bus, right? So it will be voltage E1 minus V1, then divided by the impedance. But we already changed this impedance actually 1 over C10, right? So it will be this equation. The next one, we just multiply each voltage by that admittance, will create 2 items. The second step, we redefine this one as a current of a source. So we change this voltage source to a current source. We simply define there's a constant current coming from the EMF to this substation or to this bus. So for this bus 1, we just call it I1. I1 is simply equal to the EMF multiplied by the admittance of the internal admittance. Then we can use the second circuit to replace the first circuit. We'll redraw every bus by this design. So you see we change the voltage source to a current source. So in the original circuit, we have a voltage source connected in series with impedance or reactance. But in the new circuit, we have a current source directly connected to the bus. And also we have a parallel admittance, which is exactly the admittance of the original branch. Okay, then we can rearrange the equation to be the left-hand side will be basically there's a constant current. The right-hand side will be 3 current. The one is going to the ground, right, through this admittance. That's the first item. That's V1 minus 0 multiplied by the admittance will be first current. And there are also other currents will be the current going to other neighbors. Okay, so next we can generalize this design by this figure. So for any bus, no matter how many branches, we can always take this unified design. For this unified design, we'll have like one equation to hold. So left will be the total current going to the bus. And first item will be the current going to the ground through the admittance representing the original internal impedance. And depending on how many branches we have, so for each branch, we'll have current going to the neighbors, the other branch. Because we, if we assume the system will have a totally n buses, okay, so there will be n-1 neighbors. So there will be n-1 such branches. For each branch, we'll have 1 item. So this is the little thing we did, including the step 1, using the Kirchhoff current law. Second, change the voltage source to the current source. But this is a very important step. Starting from there, in the next lecture, we'll talk about how to construct the model of a power flow. Okay, so I'll just stop here and we'll continue on Friday. Please let me.